morning everybody. So, we are having this course on smart materials and intelligent system design, in which we are specifically focusing in this module on composite materials, and this is the round 2 of the composite materials. Whatever overview we have taken yesterday in the last class, now we will be having the round 2 of it. So, here we will talk in the last one, just very briefly I had introduced you to composites, specifically smart composites, and then composite classifications, composite applications particularly, and also we have talked about various fibers. Also we have not, although we have not touched all the fibers, but we have touched some of the very important fibers, right. If you remember, what were these fibers? Glass fiber, always keep in mind, which has actually 3 different types, E fiber and the S fiber and the C fiber. So, this is very important for us to make a composite and then make it a smarter composite. Then also we have talked about carbon fiber, and historically I have touched the issue of boron fiber. And the only other thing that we have talked about are called polyaramids or Kevlars. Polyaramids are commonly known as Kevlar. So, these were the fibers that we have talked about. Today, let us see what we can do with these fibers in order to make a composite, because as I told you already that in a composite we have to have fibers or some kind of reinforcements. It need not be in the form of a fiber, it can be in the form of a chopped fiber, even smaller it can be in the form of whiskers, even smaller it can be in the form of particle, and even smaller it could be in the form of nanoparticles. So, fibers or such reinforcements that you will need, plus you will need a matrix. In fact, when you will make a smart composite, lot of thought process has to go in terms of choosing this matrix also. So, let us see and all these things. So, what we propose to study now is first of all a very quick overview of composite manufacturing technique with a special emphasis on hand layup technique. There are other 2 techniques also, resin transfer molding and pultrusion, which I will just very briefly mention each one of them. And then we will go to fiber reinforced composites, polymer-matrix composites, metal matrix composite, ceramic matrix composites and carbon-carbon composites. And also we will talk a little bit about sandwiches. So, hopefully once we do these things, you will be able to get initiated into the micro mechanics of such composites. So, very quickly we will talk about the composite manufacturing techniques. Now, there are many once again, but for the sake of this course we have made some very brief and most important techniques that are used. So, accordingly I have chosen up hand layup, because most of the times this is the most popular one, where we make the composite and we add the smart materials in that making process itself. One technique which is coming up is actually in resin transfer molding, where we are adding the smart fibers in this case in order to know what is the curing process going on when a composite is getting hardened. And pultrusion we will know, because it is very important, but so far pultrusion has not been added with the smart materials. Now, if we first look into the hand layup technique, mold preparation is one of the very important part of a hand layup technique. So, you have to first prepare a mold, over which you have to wrap basically the composite material, and then you have to make sure that the composite comes out beautifully. So, you have to have a release film on the applied on the over the mold surface, so that it comes out beautifully. And there we also put a gel coating, which is a specifically formulated resin layer, which becomes the outer surface of the laminate. You do not want the fibers to actually come out. So, we put a resin layer. So, that is the second layer. It will also give a nice glossy finish to the composite, and then we apply the fiberglass and in terms of the fibers, pre-measured the resin and some catalyst, because these resins on its own, if you want them to get hardened, it will take a lot of time. So, in order to reduce the time and to increase the network densities of these thermoset polymers, we use a catalyst or a hardener along with, mix them all together. So, it is ready, then you apply them over that fiberglass system and then you allow it to get hardened with sometimes raised temperature and also raised pressure. So, what we call an autoclave machine we actually use in order to do it, okay? And this is the process which I refer to as the curing process. Now, in the last class I have shown you these macro fiber composites, right, MFCs. As you can see that this is a aerofoil here, over which what has been done, and this is made of carbon fiber reinforced plastics, and there is a description of it 090T. What is this? We will learn gradually, but it has different directions of ply, at least that we can understand from here, and these two directions of plies we apply all these release film gel coatings and then apply the resin, and finally, we put the MFCs outside. We can either surface bond the macrofiber composite, or we can also in another way of doing is we can embed the macrofiber composite inside the system. Let us look at a very brief video in which I will demonstrate you the hand layup technique. So, this was prepared by the Remi team in Finland, and you will just very briefly see here that how they are making the composite laminates in this the process that I told you, the application of resin film. So, this one that you can see here, this is actually carbon fiber. So, you see they are cutting the carbon fiber of the desired shape. Many times this carbon fiber comes with its own resin and we call it prepregs. So, now you see they are just smoothing the surface, applying the release film. So, that is getting done, so that the composite would come out beautifully, and then it is already resin coated. So, now what they are doing is that they are doing the hand layup of the ply. So, they are cutting you can have as many number of layers as you wish. Okay. At this stage also you can actually insert the smart actuators, but if you do so you must actually have the electrical leads there. Now, they are applying a vacuum forming here, as you can see. I told you that pressure is needed. Now, you can have positive or a negative pressure. In this case, they are applying vacuum here. So, that the role of the pressure is that the resin will get very nicely uniformly wetted everywhere. So, that it is not that there is a resin pocket somewhere, more resin somewhere, less resin, and here they are using the epoxy resin, as you can see from the side. So, epoxy resin is getting applied, slowly you can see that vacuum that has been made, nicely the resin is going everywhere, it is spreading all around. And sometimes they also keep a additional bleeding pocket, so that no extra resin remains there. And now you see that they are just opening it up, the whole system, and that is where you have the disc. Incidentally, this type of discs are actually used in automobile brake discs and things like that. So, sports car have a good demand of this type of carbon fiber reinforced discs. The second one in terms of composite manufacturing is actually resin transfer molding, and in this resin transfer molding process, what we do is that we first make the preform of the fiber and then resin place this whole thing in a dry condition in a mold, and then you pump the resin to impregnate the fibers. So, you can this is the way you can actually make quick prototypes, etc. The only thing here is that the fibers, they are in all the directions. So, here you can actually artificially create anisotropy. Okay. So, here you can create anisotropy, but that means by changing the fiber angle, etc. But here there is generally you cannot create anisotropy. So, this is I would rather say homogeneous and isotropic. That is so some applications need this kind of a thing, where you need to provide fibers along all the directions, because possible sources of loading can be from all the directions. Now, how the smart materials is coming into picture? Well, this is one such thing that is very recent work is getting done, in which you can see optical fiber leads you can see here, right. All these optical fibers, we will call them as OF henceforth. These optical fibers they insert it, so that whenever this resin impregnation is happening, the optical fiber can actually give you the exact condition. Sometimes they also use other conductive wires to do that, the exact condition of wetting, how much percentage is getting wet, etc. or not. Now, that is about resin transfer molding. There is another automated process which is called pultrusion, and in this particular process what they have is that they actually have the fibers which gets pulled. So, pultrusion is actually pull plus extrusion, that is what we will call as pultrusion. So, in this pultrusion process what they do is that they continuously pull the fibers, and there is a resin pocket in which these fibers are getting dipped and then they are pulled again. So, as a result you are getting composites in the form of plate actually, unidirectional composite plates, and later on you can arrange them for various forms of laminates, etc. So, that is about a very brief introduction to the composite manufacturing technique. Now, if we proceed further, let us talk about the different types of composites that you can produce through these ways. In terms of architecture, you can have reinforcements as particle reinforcements, which can be used in resin transfer molding or such processes. You can have fiber reinforced, and that I have shown you just now. You can have structural composites. Now, in terms of the fiber reinforced, there is one very good example. This is used in magnetostrictive composites. So, magnetostrictive material, it is used both in terms of fiber reinforced as well as in terms of particle reinforced composite. Now, in the fiber reinforced composite, what they do is that they actually make FeCO fibers, and they make pattern in which I have already told you about different architectures, particularly unidirectional ones. In this case, it is a bidirectional one, in which in the fiber architecture you have a warp part, which are the straight parts, as you can see, that is the warp, and there is this weft part. Now, this warp part is made of polyester, and the weft part is actually made of iron cobalt fiber. So, you get something like that, and this is the thing that you place, and then you carry out the resin transfer molding, you get a beautiful magnetostrictive composite. In the particle reinforced one, there are two ways. One is large particles, you simply apply them just like the fibers and then pour resin over it, and another one is called dispersion strength type of a system. I will shortly give you an example of it. Now, in the form of the structural composite, there we actually build up the layers of the composites. If we keep all the layers with same fiber angle, like all 0 degree fiber angle, then we call it as a unidirectional composite. If we keep if we vary this 0 to 90 etc., then it can be angled ply, it can be cross ply. If it is cross ply, then it is generally only 0 and 90, and if it is more than that, like in this example, then it will become angle ply. And there can be another variation, which is sandwich variation, in which the core part is of honeycomb material, so that it is very light, and you apply the face sheets where you actually apply the composite material. So, you can see that this part is composite, and inside you get actually the honeycomb structure. So, these are called sandwich panels. So, it is a big realm of so many different types that you can use in composites. Now, I was talking about two examples. One is that the large particle and the dispersion strength end one. Now, terphenol D is actually used for these dispersion, these large particle based reinforcements. For example, terphenol D, which is a magnetostrictive material, you already know, it is actually mixed with epoxy resin, and the particulate phase is harder, stiffer, and this is what that impart the magnetostrictive behavior. So, this reinforcing particles will restrain the movement of the matrix space in the vicinity of each particle. So, thus the hardness is coming into picture, and the matrix role is to transfer the fraction of applied load to the particles. So, it is the terphenol D particle which works like a big boss. It actually takes the load, it also deforms itself, and matrix has to be the follower. Its role will be that all the particles are getting equal share of the loading. So, in a micro scale you can see that how these particles are getting. So, these are the particles, as you can see, these are terphenol D particles, these white parts, and all along what you have is the resin. If the particles behave the way the wares behave, then you get further anisotropy, further strengthening, etc. But to do that you have to align the particles. How do we align such particles? Well, one way to do is that while manufacturing you keep magnets, so that the particles will align themselves along these lines. As you can see that all particles are aligning themselves along these lines, and a sort of particle chain is getting created inside epoxy. As a result, you get a sort of directionality sense, which helps in a lot of way. That means, you can then have a control over the nature of deflection of the system. So, that is about terphenol D in a large particle case. Let us look into another example of dispersion strengthening. Now, in case of dispersion strengthening, particles are normally much smaller, something like in the nanometer level. In fact, that is what is used for making something which is called nano composites. So, nano composites, what is nano in it? The nano part that is in it is nothing but these nanoparticles of various passive material or active material. If the active material is terphenol D, can be also made in nanoparticles, and the one that we are particularly would like to discuss is nickel titanium nanoparticles. Now, of course, in this case the strengthening occurs at the atomic or molecular level, and as usual matrix bear in the one small difference is here with respect to the large particle one. In the large particle ones, epoxy's role was just so that the load is to make sure that the load is uniformly distributed, but in this case matrix can bear the major portion of the load. So, what kind of matrix can do it? Polymeric matrix generally cannot do it. Well, yes, the metal matrix can do it. Okay. So, these metal matrix are like aluminum matrix in this particular case, they can do it beautifully. So, metal matrix, and inside that you have these small dispersed nanoparticles which will hinder the motion of the dislocations, because most of the times the strength of the metal gets degraded because of the presence of dislocations in the metallic crystals. So, that dislocations movement side these or between the grains, if that can be stopped or restricted, then you can get a much higher strength. So, that is what is done here. So, you can see that there is a dispersion, there is a dislocation here, and you can see the stress field of the dispersion, and you have a strong particle here. That strong particle is actually affecting this movement of the dispersion, it is blocking the movement of the dispersion. It can also generate its own state of stress around, so that you can completely make it much more tougher, etc. So, you can see here that nickel titanium particles are inside and in a deformed state. So, this will be possibly in the low temperature martensite state. Now, you heat it up, okay? That means, you go to say higher temperature, immediately these fellows will try to expand, and they cannot because they are inside a matrix. So, they are going to develop sort of state of stress depending on how they are expanding or trying to expand, and that is actually generating compressive stress. So, that compressive stress, imagine that if you have a crack here. So, because this fellow is trying to expand, so there is a compressive stress from both the sides, which will not allow the crack to expand. So, thus dispersion of nickel titanium particle in aluminum matrix is a good example of dispersion strengthening. Now, we will come to fiber reinforced composites. Okay. This is the most popular one out of all the smart composites. So, here what will be the role of fibers? Well, in just like traditional composites, they will definitely enhance stiffness and strength in comparison to the matrix. They will initiate shape change in the whole system. I have shown you the macro fiber composites. So, that is one example of a fiber reinforced composite. They will also help in terms of crack bridging. We will discuss it when we talk about cell filling. They enhance thermal resistances and some other properties also you can improve through them. Now, these fibers can be of three different forms. If it is small, very small, L by D ratio wise. So, then we call it as whiskers. Okay. So, these whiskers are actually flaw free. So, that way they are having high strength, but they are expensive. There is graphite as whiskers, zirconia as whiskers, PMNPT as whiskers, and they are generally used for damping, structural damping. These are very good, okay, also for strength improvement, etc. Now, if it has L by D ratio at least equal to 10:1, then if the more the better, then it will become the fibers, and they can be polycrystalline like piezoceramic fibers, or they can be amorphous like if we develop the glassy fibers or things like that, and generally they are made of polymers or ceramics, right. Like polycrystalline fiber is a ceramic one, the active fiber composites, they use the piezoceramic fibers, also sometimes you can use the polymers. And about the other variation, that is wears, they are relatively of large diameter. The diameter that we are talking in this case, it is about micron meter range. In this case, the diameter can be less than micron meter range, okay, and in this case the diameters are greater than the micron meter range, and these are relatively large. Typically nickel titanium wear, for example, is used in terms of wears in the fiber reinforced composite. Now, what is the role of matrix in the fiber reinforced composites? A is that it binds the fibers together, that is very important, otherwise the fibers will work individually, that will not help us. It will protect the individual fibers from damage by external environment. As I told you that glass and ceramic fibers often get damaged in the handling. So, the matrix protects that. It acts as a medium to transmit and distribute externally applied stress to fibers. So, this also I told you that matrix takes the load first and makes sure that none of the fiber remains idle, they get equally loaded, and they also serve as a barrier to crack propagation. If the cracks start, they are the first barrier, and then it goes to the fibers. Sometimes it serves as conductive or permeable medium. This is very important when we will be making smart composites. I told you that this nickel titanium wear reinforced composites, if you try to make, then in that case you would see that this nickel titanium wear is to be heated. Now, by applying heat through direct electrical leads, that is something difficult, sometimes difficult to do. So, what we do is that we use a conductive matrix and we heat up that conductive matrix very easily, and then through that the nickel titanium wears are actuated. So, that is how that could be another additional role for smart composites, the matrix of a smart composite. So, the matrix in general should be ductile, elastic modulus of the fibers in general are much higher, and there should be adequate bonding between matrix and fibers. This is an area of active research, that how can you enhance adequate bonding. In fact, if you can generate fibers which can do this, those kinds of fibers are of very high demand. Now, we just very briefly look at the stress strain curves. So, matrix being ductile, as you can see that it takes a large amount of strain before it actually fails here, and fibers being brittle, you can see that it takes only epsilon f star, much less strain for failure. So, naturally we expect the composites to be somewhere in between, as you can see that it shows some amount of plastic strain before it goes to failure. Generally we consider when the fibers fail in the composite, we consider that to be the failure point. So, a composite will have two stages, a stage 1, that is the elastic stage, and a stage 2 where the plastic region will be coming into picture. So, that is the composites stress strain behavior. Now, in terms of polymeric matrix composite, we have matrix as polymer resins like epoxy, and we have fibers as I told you. So, suppose I use glass fiber, okay, E glass fiber diameter between 3 to 20 micron meter, and I can use also some additional fibers like macro fiber or active fiber or optical fiber, we can do that. Okay. So, that is what is the fiber part, and the matrix part is something like epoxy or polyester resin. Now, this is used mostly in building up automotive, marine bodies and different types of storage containers, industrial floorings. In industrial flooring, active glass fiber composite is very much used for noise suppression. The other group I have shown you, that is the carbon fiber reinforced group, in which the matrix remains a polymer and fiber is the carbon fiber system. So, here because of the carbon fiber you get highest specific modulus, specific strength, it can work in the elevated temperature, and that is why it is used mostly in all these types of sports cars or racing cars, advanced automobiles, and also advanced aircrafts like this Boeing Dreamliner. So, that is what is the carbon fiber reinforced one. Aramid fiber reinforced composites are generally used for making bulletproof jackets, as you can see. So, they are good in terms of shock absorptions, and that is why they are used in these cases, and here also we have actually different types of smart fibers we insert inside in terms of making what we today call intelligent textiles, which takes care of not only that what is the kind of curing process etc., but also what is the state of stress, whether there is a fracture already in it, then you cannot use the bulletproof jacket for the second time of use etc. So, in all these cases you would need the aramid fiber reinforced composite along with some intelligent fibers in it. Now, there is a brief comparisons. If you go for GFRP, your tensile modulus is about 45, your transverse modulus is 12, longitudinal strength is 1020 MPa. But if you look at Kevlar, it has a higher modulus, it has higher tensile strength. If you look at CFRP, you have even higher things, the tensile modulus, and you have even higher tensile strength in the system. So, that is a brief comparison between the two systems, and then we will talk about the metal matrix composite. We have talked about polymer matrix composite. Another matrix that we can use is metal matrix composite. Now, once again matrix should be ductile. So, use ductile metals like aluminum is very popular. Also magnesium, titanium and copper are used as matrix. As fiber, you need to in this case it's not the ductility, it is not just the strength, but you also need to improve sometimes the hardness of the system, fracture toughness etc. So, we put fibers as carbon fiber, silicon carbide, boron, aluminum oxide, and the last two are smart materials, nickel titanium or ferrite cobalt system. So, you see the intention here is that to improve the property of the basic matrix, like let us say aluminum. Okay. So, to improve you can give some additional hardness to the system, you can also improve its strength of the whole system, and in addition to that you can use it for structural controlling the structural deformation and things like that. So, that is what is the MMC. Advantage is that you have a higher operating temperature, it is non-flammable and you have a greater resistance to degradation by organic fluid. For many applications in space type applications, this is actually quite good. And I have given here just for your comparison sake of several metal matrix composites which are reinforced with continuous and aligned fibers like carbon fibers, etc. One important thing you have to see here is that the fiber content cannot be too high. Sometimes it is quite low. In fact, here this is the only case where it is little high, okay, and the density that you are achieving is not very low, because in comparison to polymer composite. On the other hand, you can see here that the strength that you are getting can be actually very high. Some of the cases like borons, silicon carbide, okay, borosilicate, etc. So, that is what is the metal matrix composites. Where we can use it? Well, golf balls, sports applications, one of the fantastic application is metal matrix composite. Tank armors made of metal matrix composites, space shuttles or other tubular struts, metal matrix composite. Antenna boom of the Hubble Space Telescope is made of metal matrix composite. So, quite a few high end applications. Now, we talk about ceramic matrix composites. Ceramics as matrix, they are highly brittle in nature. So, definitely they are going to have low fracture toughness. In general, for example, the fracture toughness is ceramics is 1 to 5 MPa root meter, and whereas metal alloys 20 to 90 MPa root meter. So, if I mix metallic fibers in ceramics, then I am going to increase the fracture toughness of the ceramics, and that means the crack initiation which will normally occur in this case in the matrix space. So, that will be hindered by the particles, fibers or whiskers. I have already shown you how dispersion strengthening can happen by using actually dispersed nickel titanium particles. So, that can be applied in ceramic matrix in order to increase the fracture toughness. So, there are different types of ceramic inserts where we make it of ceramic matrix composites, or brake disc of Ferrari race car, that is of ceramic matrix composite. Now, finally, we talk about carbon composite. They are very expensive, because they are unusually high in terms of modulus of elasticity, strength, specific modulus of elasticity. Suppose you go up to 200 GPa with as light as close to the density of water, you can imagine that what is the kind of lightness versus stiffness we are talking about, and the temperature resist up to 2000 degrees centigrade. So, this is some of the fantastic very advanced materials that has been created by these material specialists. So, low density, high thermal conductivity, I told you that that is a good thing that can be used in terms of activating shape memory composites, low coefficient of friction in the fiber direction and high abrasion resistance. There are a lot of defense based applications, lot of them at space shuttles for example. So, carbon composite is very much used in all these advanced applications. So, this is where is the general polymeric matrix composite. Now, I just introduce you to the concept of structural composites, and here you can have many variations based on the variations of fiber angles, like if it is theta equals to 0 degree, you get unidirectional laminate. If some other angles, you get the angle ply laminate. If it is 0 and 90, you get the cross ply laminate, and there is another thing that is possible, that you arrange them in a symmetric manner. Now, symmetric manner with respect to what? With respect to the geometric midplane of the system. Like if you look at this, that you have 8 layers, 0, plus 90, plus 45, minus 45, and then again minus 45. So, you have 1, 2, 3, 4 layers here. This is the line of symmetry, minus 45, plus 45, plus 90, 0, exactly the symmetry. So, you can actually take half of it and put a S to say that this is a symmetric laminated plate. So, you can develop, later on we will show that what is the advantage of developing symmetric or asymmetric plates. So, this is a symmetric laminate plates, for example, 0, 45, 90 symmetric, and then if you have 45 minus 45, generally we group them as plus minus 45, another shortcut that we take. If there are 4 zeros, generally we put them as 04, another shortcut we take. If there are 2 of plus minus 45, we tell them as plus minus 45 2. So, to quickly refer them. And antisymmetric is a peculiar case where it is actually that with respect to the mid plane, you actually lose the symmetry of the system. For example, look at this one, that with respect to the mid plane, here one side is minus, another side it is plus, reverse. Okay. Whereas, if it is like this, then it will be a symmetric laminate. And quasi isotropic laminate, where you have equal angles between each adjacent lamina. So, for example, 0 plus 60 minus 60 or this one. So, these are all quasi isotropic, they are generally isotropic in plane. So, these are different descriptions of the composite laminates. Now, the last thing is the sandwich panels. In this case, what we have is that a strong and stiff face sheets that we have, okay, and then adhesives and the honeycombs. So, honeycombs gives the lightness and also it gives these active sheets at far away. So, this is used very much in applications like constrained layer damping, okay, CLD we call it, or ACLD, active constrained layer damping. We use this type of a system. In fact, when I will talk about one of the applications of vibration control, I will talk about how you can develop such a thing using ACLD type of systems. This is some of the applications of this type of systems, generally for housings etc., because it is very light, but sandwiches are now also applied in space applications. One last thing is the hybrid composite. In fact, all the smart composites are by default, generally they are hybrid composites, because they have different kinds of fibers in it. They have passive fibers, also they have active fibers. So, they become hybrid in nature. So, whenever more than one fiber comes into picture, it becomes hybrid. Okay. And these fibers may all be aligned and intimately mixed with one another. That is one of the objectives, so that they work integrated way. You can see one of the example of a hybrid fiber composite here, where you are using boron fiber, carbon fiber, glass fiber, all of them together. So, many applications are now coming up in which we use the hybrid composite, which is invariably more expensive and it is more difficult to actually fabricate such systems. So, this is where we will put an end to this lecture. In the next lecture, we will concentrate on the micromechanics of composites and further to the macromechanics. Thank you.